Okay, so last week we looked at computable sets, that's decidable sets. Now we're looking at sets of natural numbers rather than sets of words, as we were looking at the start of the course. We saw various properties of decidable and semi-decidable, that's computable and computably enumerable sets of numbers. And today we're going to continue the study of this kind of abstract computability theory, looking at properties of numbers and functions on numbers and things like that, and asking what properties are decidable and what properties are semi-decidable and which properties are neither decidable and semi-decidable and this sort of thing. Then next week we're going to also continue a little bit further in this vein, so doing what one might call core computability theory about computability on the natural numbers. So the material in today's lecture is the technical material. It's a little bit technical, but there's not that much of it. So the notes today are 3 pages only, less than 3 pages. The notes, then, they're rather concise, but they're also a bit dry. They don't really try to motivate what they're doing. So I want to start the lecture with quite a long introduction today, which isn't in the notes, essentially motivating the kinds of questions we're going to consider. And then we'll move to the technical part, which will be technical. But even before getting to motivation, I just want to remind you a little bit of a couple of things we've done in the last week. It's also to make up for an omission from last week, something I forgot to say. It's not very in the middle, but never mind, it'll do. So last week we were considering computable and computably enumerable sets, and we had these theorems that characterize the computably enumerable sets, that's the semi-decidable sets of numbers. The first theorem characterized the computably enumerable sets as the domains of partial computable functions or computable partial functions. And that gave us an enumeration of the computably enumerable sets. So we had the enumeration E, a natural number, maps to W sub E. So this is W sub E is the domain. Computable partial function phi sub E. What I forgot to mention, well, we had a theorem towards the end of the lecture, which was the computably enumerable sets could also be characterized as the ranges or images of computable partial functions. And that leads to a different enumeration that's nonetheless an enumeration of the computable partial functions. And in this case, the standard notation is to use capital E for the notation, for the range of the computable function phi E. And I'm using E just to emphasize it's a natural number, it's framing over natural numbers, but to emphasize we're using it as an index of a computable function. So this is E sub E, which is the range of phi sub E. And as I said last week, and I'm mnemonic for remembering W, so that I think of the M in domain, remembering the notation, which one's WE and which one's ME. I think of the M in domain, and I then invert it by 100. Let's reflect it in the horizontal in the XY, reflect it in the X-axis, and rather than rotating, then we get to W. And here I remember this with the E, which is of course already an E, but we can also reflect that to the x-axis, which is why let's do it that way. Anyway, so that's why we get. So what we have is two natural enumerations of the computably enumerable sets. And because these are total surjective functions, then that map us from the natural numbers to well, the set of computably enumerable sets. So the set of all sets of numbers, which that A is computably enumerable. Here we have E maps to W. Here we have E maps to E. So you might remember in the third lecture, we had these representations of sets in terms of representing elements of sets using names, where we name sets by sequences. A few lectures ago, I remarked that one can replace representations where we use sequences as numbers, words as names, not as numbers, use words as names, can replace them with representations using the natural numbers, and from now on we're going to consider representations in this form. Essentially, we've got two different natural representations for the set of computably enumerable sets. And in fact, these two representations are equivalent, meaning the identity function between them has a realizer, meaning that in this setting there are computable functions in both directions that make the two triangles compute. So commute. So the composites in all directions are the same. Now I meant to check this actually before the lecture, and I went back to my office to do it, and somehow then I got distracted by something, so I forgot to. I believe establishing this equivalence may be an exercise in today's exercise class. If not, then it'll be probably in some future exercise class. But anyway, just to remark, we have two representations, but in some sense it doesn't matter which one we use because they're equivalent, they're computably equivalent. But of course, when we use one, we need to know which one it is. So don't get the two off muddled. Right, so these are representations of something of interest, the computably enumerable subset of natural numbers, named or equivalently the semi-decidable subsets of natural numbers. Today's lecture is going to be concerned with a different representation, which is one that we've seen already earlier in the course, which is the representation of the set of computable partial functions. And because this set is going to be important throughout the lecture, we'll give it a name, and the traditional name in computability theory is curly C, curly capital C. Sometimes you add a superscript if you want to say computable partial functions in 2 arguments or 3 arguments or so on, but we're just going to look at the unary one, so we won't bother even defining the one with superscripts. So this is a set of partial functions on the natural numbers such that f is computable. Okay. And we have a natural representation of this, of course, which we've already seen. And again, it's a total representation, so it's a total surjective function from the natural numbers to the set of computable partial functions. So let's see if anyone's super awake. So can somebody tell me what is this map here?
So it's was it psi or something?
Nearly. Fine. Yes. But excellent. So thank you. I'm very impressed. You've only just taken your coat off. So immediate participation. Very good. So this is E maps to phi. of P. Psi is our notation for the universal computable. Psi U. Okay. Now, I want to mention one way of looking at this picture, just because the technical questions we're going to consider seem a bit abstract, but to try to emphasize that they are related to questions in the real world. So let's think about how this E maps to phi sub E works. Well, we were enumerating the computable partial functions by viewing E as a code, natural number code, for a word, and then viewing that word as a code for a Turing machine, with our representation of Turing machines from the second lecture. So E is we have E, a code, natural number code for a code, a word code, natural number code. This is a code in the universal alphabet, for a GM. Well, the coding is, of course, incidental. It's just a way of packaging things up as the relevant thing in question, a word or a natural number. So really, we're viewing these natural numbers as Turing machines. Okay. And these are, of course, these are just functions. And I want to emphasize the following analogy with computer science. So a Turing machine is an algorithm. So it's specified, it's got a finite specification, and that finite specification is giving the rules for how it computes. It's essentially not dissimilar from a computer program. And in fact, as we saw with other models of computation, some other models of computation are much closer to computer programs. So lambda calculus, for example, or register machines. The register machines are described by programs that are a little bit like machine code programs, for example. Anyway, so one can view this as this is kind of analogous to a computer program. And in particular, it's basically just the mere definition of the Turing machine. So we can view it as the program syntax, sort of how we write the program, plus the rules together with the compiler, if you like, how we know how to compute it. Let's call this program syntax, how the program is written. The function, on the other hand, this is what the Turing machine actually does, so how it computes. So we might say this is kind of analogous to program semantics. So semantics means meaning, and program semantics is how a program, some mathematical way of describing how a program behaves. And in this case, we've got Turing machines, if we like, or computable or partial recursive functions. So programs are very simple, and the only kind of computable behavior we have when we view things as programs on the natural numbers is partial functions. Well, of course, we've got the decidability question, but for the moment we'll focus on partial functions. So the syntax is be represented as a natural number code, and the semantics is how the program computes. And what we're going to ask, so today's question, is in here. I think I should move the camera. So today's question is, when is a subset of curly C decidable or semi-decidable? Today's main questions. And it's a subset curly B of C, so a set of partial functions, a set of computable partial functions when is it decidable? And when is it? But the reason this is such questions that are interesting with respect to this picture is if we have a decidable subset of the set of functions, well, what's that going to mean? Well, we'll come to the technical definitions soon enough. But we already, if we remember the lecture on representations, we already know what it means, but I'll expand in detail what it means in this case. But anyway, essentially what it means is, if it's decidable here, what it means is given some program syntax, namely a number E, we have a decision procedure that will tell us, yes, this program is indeed a program for this particular function, or no, it's not a program for this particular function. So, so we can view the function as a sort of specification for a program we want to write, or the set of functions as a specification for potential programs we want to write. And the question is, can we actually test the program to see whether it matches our specification? So, and if we can just test it with yes and no answers, then it's decidable. If we can at least halfway test it with just yes answers, but with potential loops in the other case, then it's semi-decidable. So that would be useful properties, if we can, essentially, we might want to implement a particular function, and we might want to implement a particular function, say the factorial function or something like that, and we write some complicated program for it, like some complicated Turing machine. We want to check that it's done. In the case that if it was decidable that a program computes the factorial function, then we could just input our program into our program tester, and our program tester could tell us, yes, that's a factorial function, or no, you made a mistake. So potentially, these questions could have applications in testing the correctness of programs and this sort of thing. At least they could if they had positive answers. If you could give them positive answers in interesting cases. So maybe let me go to the definition of what it means to be decidable.
Does this have anything to do with like specifying program behavior with random types? Maybe we see it as a lifting this problem because
but it has to do with specifying program behavior. In this context, the specification is simply a set of potential partial functions, which is, a set of partial functions, which is our sort of the target of the specification. We'd be happy with any one of those, or alternatively, we'd be unhappy with any one of those. So then one could use whatever mathematical means one liked to specify programs, so dependent types. There are other issues. So one wants to talk about dependent types and specifications, and then there's this whole use of that framework where a type is a specification and the proof of the inhabitant of the type is a program meeting a specification. That's a whole different area. There are of course connections, but I don't want to get into the something to discuss in the break, not directly related. Because not directly, but there are all sorts of interesting connections, but not during the lecture. It's an interesting question. Anyway. Okay, so we've got a subset of computable functions. We want to say what it means it to be decidable or semi-decidable. So we have the definition of that from lecture 3 on representations, adapted to the case. We have a general definition adapted to the case of this particular representation. Let me just tell you what that means in this case. So B, a subset of C, is decidable. This is the definition. Well, decidable means, so here I'm going to put the simplest possible mathematical condition that's equivalent to this. But let's just go through the definition. So the B is decidable if we remember the definition from the representations, if there exists a computable function from C, the set of computable functions, to 2, which was the set 0, 1, such that the inverse image of 1 is the set B. So, or rather, why am I being so complicated? If the characteristic function, function I curly B, which is a function from C to 2, where I'm using 1 to represent truth value there, is computable. And what computable means is we have our representation of C, and we have 2, which has a very simple representation just by the identity. I mean, this isn't the one that Deborah likes in the exercise classes, but anyway, for me, we'll have the representation that this is just the identity if x is less than or equal to 1 and undefined otherwise. Here we've got my representation, and here we've got we want the characteristic function, and being computable means we have some computable function here, from which needs to be total, because this is the total representation, by the total representation. We have a computable function here, such that this diagram begins. Okay? But what this amounts to is, well, we've got a number here, because 0 has a single number representing it, and 1 has a number representing it. This function is actually uniquely determined what this function needs to be. So we're simply asking, is this function computable? And because that's a function from the natural numbers to 0 and 1, asking is this function computable is, from last week, the same thing as asking, is the set of things sent to 1 a computable set, namely a decidable set? So what we get is B is decidable, the subset B is decidable if the set of codes for elements of B, which is all the things we need to send to 1, if that is a computable set. So if we call this is called I sub B, computability theory, a set of indices for the set B is a computable set. So where I sub B is a set of all indices for functions in B. So those indices E, numbers that represent functions in B. Okay. And similarly, I won't go through the argument and picture again, but if you work it out, so remember, we call a subset of a represented set semi-decidable if the partial function, Looks like the partial characteristic function is computable, and that simply amounts to, if you go through the definitions, and I'll leave it for you to do yourselves, if I sub B is computably enumerable, so it's a semi-decidable set. Okay. So that's what it's about. And even if you don't remember all the details involving representations, actually these two characterizations are very easy to understand in their own right. It's natural to say we can decide the set C, we can decide the set B, very natural definition of that, if we have a decision procedure that, given the program B, will tell us whether it's an index for, given an index E, which we think of as the syntax of the program, will tell us whether the function it defines belongs to B. And the same kind of reasoning is semi-decidable. So if we have semi-decision procedure, that's the same as saying from last week, that's the same as saying the set is computably enumerable. This is saying we have a semi-decision procedure that works on indices. Okay? And our first theorem, Rice's theorem, is going to characterize the decidable subsets of the set of computable functions. So we'll find out which properties we can specify of a program that we can have another program, which is a sort of test program, if you like, that will decide for us whether or not the program meets our specification. Okay? And that's going to be called Rice's theorem. The answer to this question, which properties we can do that, find such a decision procedure for. So let's just think about this isn't the first time we've met such a question, actually, just we haven't seen it in this way. So let's think about some interesting such specifications we might have. So some interesting sets B. So the first one, let's call it B0. Set of those computable partial functions such that f of 0 terminates. So given an index for a partial computable function, can we decide whether or not f of 0, the partial given an index E for a partial computable function, can we decide whether or not phi of E applied to 0 terminates? Do you think? Why not? What's this an example, an instance of?
So we could reduce the halting problem.
Yeah, so this is basically like the halting problem. But this is sadly undecidable. It's basically the halting problem. So we can't decide that one. Let's call this B1. And if someone's taking notes, that'd be useful because I'm just making up this numbering system from the top of my head, but I might want to refer to it later. So, I mean, the order I'm doing it is just it occurs to me, but so the second one, let's weaken this. We're not going to require f of 0 to terminate, but can we test if there is some number such that f of n terminates? So there exists an n such that f of n is defined. Program terminates. So I don't know if you've considered this set, but it won't be a surprise that this is again undecidable. Okay? Because there's some termination in there. And something that we did consider in a couple of, maybe even last week, but in a recent lecture anyway, was the set f in C, so those partial computable functions, but a total. So for all that. I mean, you can imagine this should be harder than all the others, so it's no surprise too that this one is undecidable. And lastly, we see the bottom of the board yet. So lastly, I'm going to squeeze it here. Let's suppose we're trying to specify a particular function. I'm just going to use the factorial function just as a random example, but it doesn't actually matter. So let's try B3, curly B3. So that's all those computable partial functions, well, or rather, it's a silly way to write it. It's the singleton set consisting of a function n mapped to n factorial. Okay, so this is, can we meet, this is really a tight specification. We've been doing these sets of specifications. We're specifying a single function that we want to write a program for. And we want our decision procedure to tell us, yes, you've written the correct program. However, do you think this is a decidable set? No, it's not. Again, this is undecidable. Now, we're not doing very well in finding decidable subsets of things. But let's consider semi-decidable. Well, let's write semi-decidable in green. So is this one semi-decidable? Yeah, indeed. So people nodding, and indeed, because we get our program, we apply it to 0, we run it, we wait to see if it halts, and if it halts, then we say, aha, it halted. So we know it halted. So we know it's behind the map of 0. But this is at least semi-decidable. What about this one? Is this one semi-decidable? That there exists a number. Okay, well, some more nodding, but why is this one semi-decidable?
We can do the parallel.
Yeah, we can do this, there's a parallel search for some number. But this is, plus we also saw that things like this were semi-decidable last week, so search semi-decidable. What about this one? Is this semi-decidable? It's not, because now we need to test it on all numbers. And I think we might have already seen, I think we might have seen a few weeks ago an argument that this was not semi-decidable. So this is not semi-decidable. Let's put that in orange. And what about this one? Does anyone have a feeling for whether this is semi-decidable or not? So it's not going to be semi-decidable because essentially what you need to do, there's no clever way of doing it. And if you were doing it naively, you need to check infinitely many things, and you can't check infinitely many things. Like you need to check it's correct on infinitely many arguments. This is again not semi-decidable. And in fact, so most useful things we want to specify are not semi-decidable. And that's just a shame, but that is how the real world is. And what it means is that program verification is a tricky process. And yeah, there is a lot of research that goes into developing methods for program verification. So that's kind of the real world relevance. In the end, it's not so real world relevant because verification is more difficult than that. But how do we know this? And this is where computability theory is going to tell us we can't do this. So we need to try other things. So today we're going to have two results. Rice's theorem, which explains the undecidability results, and the Rice-Schapiro theorem that that gives a property that always holds once you've got semi-decidable, and which allows us to show that these two, that property allows us to conclude that these two examples are not semi-decidable. Okay. So I'm going to state Rice's theorem, and then mention some side remarks associated to it, then we'll have the break. And then the next hour is going to be the proof of Rice's theorem. So then after the break, we start getting technical. So Rice's theorem. A subset set B of computable partial functions is decidable if and only if. Well, can anyone think of any decidable subset of the set of computable partial functions?
I think so, it's decidable.
Single set. No, so finance no good. The empty set, that's decidable. Yeah. Okay. The others? Sorry?
So,
C itself, the whole set, yeah. That's it. Okay. So you don't, there aren't many interesting positive answers. So just a little side remark associated to this. So if we look at the, most people in the course of these side remarks don't, it doesn't matter if you're not interested in all the side remarks. It can just be a time for you to reflect on your own thoughts or so on. But for those who do like side remarks, one can look at the represented sets and computable maps between them, and these form a category. We've actually got computable partial maps and computable total maps. And decidability, so we've got, I'm not going to write the whole representation, but decidability, so the decidability, the subset there in one-to-one correspondence with the characteristic functions, so we can view the decidable subsets as total computable functions from the set of the represented set of computable partial functions to the two-element represented set. Okay? And in fact, this is saying there are only two such maps. But more than that, those two maps are the constant map. So it says whenever you have a computable total function from C to 2, it factors through the one-element set, or the terminal object in the category. Okay. There's always a map here. So any computable function here factors through the map to the terminal object. And there's a category theoretic name for this kind of property. This says that the object 2 is orthogonal to C. And hang on, maybe yeah, well, let's put it like that. I'll think about that in the break. Anyway, one can view it in this sort of factorization property. Okay, but anyway, that aside, it's quite a stunning result. It tells us decidable subsets of things like computable partial functions are just not interesting, but we need to understand why that is the case, and we'll understand that when we see the proof. It's 2 minutes to 3, so we'll start again at 13 minutes past. Are there any questions? Okay, let's take this offline then. Okay, so we're going to prove Rice's theorem, which is off camera, but it was on camera before. I've now moved it to the left-hand part of the board. So the only decidable subsets of the set of computable partial functions are the empty set and the whole set. And to do this, we're going to need a very simple technical tool, which will be useful throughout the rest of the course. This is the technical tool of reducibility. People who've done courses on computational complexity theory will have met similar notions before. This notion of reducibility is going to be like the kinds of notions of reducibility one considers in computational complexity, only without any complexity constraints. So, for example, in the notion of NP completeness, a very famous concept in complexity theory, is based upon reducibility, but these reducibilities involve polynomial time computability. In our case, we're going to have reducibility, but just via computability, but without any resource constraints. So no time constraints, no space constraints. So we say that this is a definition, so that A and B, let's maybe put the assumptions in different places so the definitions can be on the top. So we'll assume that A and B are sets of numbers, and we say that A is reducible to B. Now, there are many notions of reducibility in computability theory. This notion is what's called many-one reducibility. And it's also called total reducibility because it's going to be reducible by a total reducibility in terms of a total function. So many-one totally, let's put that in double brackets because one often says many-one reducible, one doesn't often say totally at all. But anyways, many-one totally reducible, but all that stuff's in brackets because I'm going to henceforth just say reducible to B if we can use B to test membership of A. And what that amounts to is if there exists a well, because it's totally reducible, we're going to ask for a total computable function. F such that, and the point is, for any natural number, we can test if it belongs to A by applying F to it and testing if it belongs to B. So for any natural number n, sorry, n is belongs to A, it can only get F belongs to B. It's as simple as that. Just to remark, in exam situations in the past when we've been to do with reducibility, people sometimes forget that the quantification here is over all natural numbers, not just over, I sometimes see answers like all n in A, f of n is in B, and answers like that. It's really important to quantify over all natural numbers here and have this equivalence. And why is this useful? Well, as I say, you can reduce membership in A to membership in B. So I don't know if it's a lemma or a proposition in the notes. Let's be consistent. So lemma, the reduction lemma. By the way, there's notation here, which also I'm not using in the notes, but maybe I'll use it later. But people often write A sub A less than equal to sub n b, the n for many non-reducible. That's just the notation. The reduction lemma says, firstly, if A is reducible to B, and B is decidable, or it's computable, which is the same as decidable, but we're talking about sets of natural numbers, then so is A. And secondly, if A is reducible to B and B is computably enumerable, so semi-decidable, then so is A. I won't write out the proofs, but the idea, they're very simple, and the idea is the same in each case. So, for example, if A is reducible to B and B is computable, we want to show that A is computable, so we want to decide membership of A. So given a natural number, we want to decide does the number belong to A? Well, we don't know how to deal with A directly, but we have this if and only if, so we apply our computable function f to n. B is computable by assumption, so we test its membership there, and that gives us by this equivalence, that gives us the answer, does n belong to n or not? Okay. So just to say in the notes, there's a weaker notion of reducibility, which is partially reducible. Let's rub out the many one, and let's have partially. So this is now an option, an alternative. This is a different definition. We're either going to have partially or totally reducible. Okay, and in the case of partial, we're having a notation. We put the little p superscript here to say that you're being partial. And you can probably imagine what the definition, what the change is when you have partial. You simply require this computable function to be partial, not total. So it's more general. Okay. And the rest is the same. But notice in the partial case that n belonging to A, we need f of n belongs to B. So that means that the set A needs to be contained in the domain of definition of the partial function, because f of n needs to be defined on that. And part 3 of the lemma, which is in the notes, is that two separate lemmas in the notes, that if A is reducible to B and B is computably enumerable, then so is A. So notice we can't use a partial reduction to decide membership of A, because if we apply f to an arbitrary n, it may be undefined and we'll go into a loop and never get an answer back. That. The colour before, but now the notation. Right. Anyway, so in the notes, partial reducibility is a bit more light than I've done it in the lecture. Actually, I don't think reducibility theorists tend not to consider it, and I don't think we'll ever have a need for partial reducibility. So we'll just deal with total reduction. Anyway, so this simple concept of reducibility is going to allow us to prove Rice's theorem. Right, so how are we going to go about it? if the Rice's theorem involves two implications. But the right to left implication simply says that the empty set and the full set of computable partial functions are decidable. That's trivial because the empty set is decidable by the well, this characteristic function is the constantly zero function, constantly false function if you like, and the characteristic function being the constantly one function, both of which are computable. So that's trivial. I'd like to just say that's trivial. So we want to prove the other direction. So suppose B is decidable, we want to prove that it's either empty or it's the whole set. So what we'll do is we'll assume that it's neither of those and we'll aim for a contradiction. So suppose that the empty set is a proper subset. I use this symbol that a lot of people use just for a non. I use this for meaning a proper subset of B is a proper subset of C. And we seek a contradiction. Okay. So the next step is we consider the everywhere undefined partial function. And we ask, is this in B or is it not in B? And actually, without loss of generality, we're going to assume that it is in B. Well, actually, when I say we seek a contradiction, we haven't. Let's just let's put this positively. We'll show that the set IB, all indices for functions in B, is not computable. In fact, we'll show that it's even not computably enumerable. Sorry, hang on. I'm in the wrong program. Yeah. Is not computable. That's better. Right, okay. So, as I said, we'll consider the empty set. There's not the empty set, the everywhere undefined partial function. So, for now, without loss of generality, let's got the yeah, thank you. We can assume that this, which is the everywhere undefined, which is just my notation for the everywhere undefined partial function, the everywhere undefined partial function, I suppose that this function is in B. Actually, sorry, not in B, in the complement of B, within C, so it's outside of B. Why is this without loss of generality? So let's put this is like a side argument explaining why this is without loss of generality. So if this weren't the case, so when this is not the case, so otherwise, F0 belongs to B. But in that case, we can repeat the whole argument below for the complement of B. But then apply the argument we give to instead prove that I of the complement of B is not computable. Now, the argument we give below, not computable, because of course, in this case, F empty set is in the complement of B. So we can just apply this argument to the using, instead of B, we use the complement of B. And then if I of the complement of B is not computable, if a set is computable, as we saw last week, its complement is also computable. And the complement of I of the complement of B is just I of B. So therefore, I of B, which by the way, as I said, equals the complement of I of the complement of B is not computable. Okay, so that's explaining why we can assume this without loss of generality. The main bit of the argument is the stuff that I'm going to do in black. So the black part, we've assumed that F0 belongs, so F of the everywhere undefined function, F of the empty set belongs to the complement of B. Yeah, so where are we? Okay. Now B is a non-empty set, so we have a function F0 in the complement of B. But the B is a non-empty set, so we can choose some function G belonging to B. So choose some function G belonging to B. And what we're going to do now is we're going to use G to define a reduction, that's a total many one reduction, from the index set of B to the halting set K that we, so remember, okay, well maybe I'll write it when we get to it. So we're going to define, this is going to be, we're going to prove that this is a reduction from, or that something related to this gives a reduction from the index set for B to the previous halting set from last week, K. And to do that, we consider a two-argument function. And we just make some clever definition. So K is Kleeman's halting set. And we define this two-argument function f of x of y to be g of y, where we're using our chosen function g. Sorry, so this is if x belongs to K. And undefined otherwise. So remember, let's put it down at the bottom of this board. Remember, K is Kleeman's halting set. A is Kleeman's halting set, which was the indices for all partial computable functions that are defined on their own index. And from last week we saw K is CE. K complement is not CE. And K, because it's not true that both its and its complement are computably enumerable, that means it's not computable. So K is not computable. But it is computably enumerable, and that's important here, because the point is this is a computable partial function in x and y. Given an x, we test using the semi-decision procedure if x belongs to K. And if it does, we'll eventually get a yes here. And if we get to yes, then we apply the partial function, computable partial function g to the argument y. Okay, so that's perfectly computable. So choose some function, define f, and clearly f is computable. Computable partial function. Because g is computable and k is computed in Europe. So clearly f is computable. Okay. We now use our friend, the SMN theorem, that I think was the subject of last week's exercise class to a large degree. So by now it is our friend, hopefully, to convert this function in two arguments to a function in one argument. So by the SMN theorem, we can consider this, we can separate out the arguments here, and that we get that there is a total computable S, that's a function, total function on natural numbers, guaranteed by the SMN theorem, such that, and remember the SMN theorem allows us to compute a two-argument function one at a time by putting the first argument into the index of the computable partial function. So here we consider x, we apply s to x, and that computes an index for the computable partial function that is in the argument y with that x already fixed. Okay, so this applied to y is the computable partial, is the partial function fxy. What I'm going to show you is that S is a reduction from the index set of B to K. So I need a bit of space here, so let's do it here. So then what we have is, if we consider an X belonging to K, then we consider function phi of s of x. So then phi of s of x applied to y gives us f of x of y. But because x belongs to k, this first condition always applies. So it gives us, for any x in k, phi of s of x applied to y gives us the function g of y. That means this is the function g. Okay? And g was chosen to belong to B. So that means that s of x, so g belongs to, so phi of s of x belongs to g. So that means the index for g, or any index for g, belongs to I of B. The set of indices for functions in B. So that means s of x is an index for g, so s of x belongs to I of B because g belongs to B. On the other hand, if x does not belong to k, then phi of s of x. If x does not belong to k, phi of s of x, that's the function in y for this particular x, the function in y, f of x, y. Which function is it? Yeah, it's the everywhere undefined function, which is our f0, f empty set. So this does that s of x. So f of empty set by assumption is in the complement of k. So it's in the complement of B. This says this belongs to complement. So this is really not in the. Well, let's just put it like this. this does not belong to an index or a function in B because the empty set doesn't belong. And we see these two chains of implications give us that X belongs to K if and only if S of X belongs to B. So S, I think I was, in my explanation earlier, I think I was saying it the wrong way around. We're not reducing B to K, we're reducing, so S gives a reduction, gives a total reduction. From K to the index set for B. But then if the index set for B were computable, K would be computable, and we know it's not B. Okay, so IB is not computable as K is not. By statement 1 of the reduction lemma. Okay, and that's it. That's Rice's theorem. So it's not such a complicated argument. The question is, where does this come from? It's just the kind of clever thing that's needed. I've never found a good way of explaining sort of why the argument has to be like this, but it works. I mean, essentially, we've got some intermediate set here. We've got something on one side, and we choose something else on the other side that we can manipulate to prove that there's no decidability involved. Right, okay, so that's Rice's theorem. Are there any questions on that? Right. Okay, so the last theorem today is a second theorem with Rice's name in it, which is the Rice-Schapiro theorem. And what this is going to do is Rice's theorem confirms it gives a reason, an explanation for the empirical fact that we were struggling to come up with decidable sets of computable functions earlier when we were considering examples. We did find some semi-decidable sets of computable functions. So obviously, semi-decidable is a bit more subtle. We're not going to just have some result that tells us that there are only these. Well, anyway, we're not going to have such a simple result. But the Rice-Schapiro theorem tells us that any semi-decidable set of partial functions has to satisfy some very strong property. So let's just rub off Rice's theorem. So this is the Rice-Schapiro. I'm not sure I was uniformly saying the right thing just now, but anyway, this is the Rice-Schapiro theorem. So it says if you've got a semi-decidable set of functions, following holds that for all computable partial functions, f belongs to B So F belongs to our subset if and only if there exists some finite function let's put it like this. It might not be exactly the same as written in the notes, but it's the same meaning. There exists some function in B such that f prime is finite and f prime is a subfunction of f. So I need to define what these two things mean, and then we'll have a look at the explanation for it. Let me just see how it's written in the notes. Okay, pretty much okay. So we're dealing with partial functions. You can view partial functions as graphs. That's sets of pairs of natural numbers relating the domain element to the most one codomain element that they're mapped to. And the subfunction relation is simply the subset relation on graphs. Yeah?
Sure. This is probably equivalent to B being this set, right? Like the set B is like F, and then the condition there exists F prime. Oh, but it's defined in terms of itself, so that
Well, it's not defined in terms of itself. It's given, and it's a property it needs to satisfy in terms of itself. But it simply says, if a function is in B, then any finite subfunction is in B. Sorry, not any finite. Then there exists some finite subfunction in B. And if you've got a finite function in B, then any superfunction belongs to B. But I haven't said what a finite subfunction is. So for partial functions, natural numbers to natural numbers, write that f prime is a subfunction of f. That's simply all natural numbers. So it's simply the graph of f prime is included in the graph of f, but that simply means for all natural numbers. If f prime is defined, then so is f, and they equal. And because we're using equal to mean is defined, we can simply write it this way. So f of n is defined and is equal to f prime of n.
Can it be f prime defined or f defined? F prime is a reduction of f, correct?
So it's not a reduction. F prime is a subfunction of f. We're viewing it as a viewing it as a graph. It's a subset of the graph of f prime is a subset of the pairs of f. So it's exactly this, that if f prime is defined, then so is f. But f's a larger function. It's defined in more places, or over whenever f prime is defined, f agrees with f. Okay. So just in particular from this notation, if f prime is defined, then so is f. Okay. And so that's the subfunction relation, the subpartial function. F prime is finite if, guess what that means? It's defined, yeah. So if I was writing it like this, the domain definition of the domain of f prime is a finite set. Or equivalently, here it is a graph. The graph is a finite. This is also a finite set. Notice that any finite function, partial function, is computable because you can simply it's defined on only finitely many arguments. So you can make a Turing machine that basically does a finite number of if then else statements. It checks for any of the finite elements in the domain if they belong to checks for any number, if it belongs to any of the finite elements in the domain, and it does the right thing. It's basically just a big lookup table, so to speak. Okay, and so the Rice-Schapiro theorem, let me try and say it once again. That's the dirty red, but it will do. If we have a semi-decidable set, then on the one hand, whenever you have a function in it, in the set, there needs to be some finite subfunction in the set. And in the other, whenever you have a function in C, for which there exists a finite subfunction in the set, then that function is in the set. So that means that whenever you have, so the left to right implication gives us that there are necessarily plenty of finite functions in the set. And the other direction gives us that whenever we have a finite function in the set, finite partial function in the set, any larger partial function is also in the set. Okay? So with this, we can immediately see that the set of total functions is not going to be semi-decidable, because there are plenty of total functions, and for none of them, none of their finite subfunctions are in the set, because no finite function is total. Similarly, the factorial, the singleton factorial, is not semi-decidable for this reason, because once again, the factorial function is in the set, but no finite subfunction is in the set, because we only got one partial computable function in the set. Also, the set of non-total partial functions is not semi-decidable, because although there are lots of finite functions in the set there, all the finite functions are in the set, the right to left implication does not hold, because consider the identity function, well, all its finite subfunctions will be in the set, but it is not in the set, so the right to left implication fails. So lots of sets can be ruled out, lots of sets can be proved to be not semi-decidable using this statement here. And just one other remark to make, this is an if-then. It does not follow, it's not true that every set B that satisfies this condition is computable. That is true in a suitable constructed universe where something called the formal Church's thesis is valid, and under that case, this is an if and only. But in general, there are very non-computable sets of functions that satisfy this condition. Right, well, it's very early, but what I propose, this is a natural stopping point, because the remaining thing to come is the proof of Rice's theorem. So apologies for those who are going to bridge that I'm stopping at this point, although maybe it's not an apology, maybe you can yeah. Anyway, we shouldn't talk about bridge on the video. So are there any questions on this part? Right, good. And the next hour is just going to be the proof of the Rice-Schapiro theorem. It's not going to take the whole hour. So again, this is going to be a shorter lecture than but it's not going to take the whole 3 hours. All right, so all I want to do in the remaining part of the lecture, and it's not going to take that long, is to prove the Rice-Schapiro theorem. The basic idea of the proof is going to be rather similar to the proof of Rice's theorem, in that we're going to aim for contradiction by reducing by showing that certain sets that if they were showing that certain sets are reducible from K, the halting set or its complement, and that the various properties we're looking for would contradict the known properties of the halting set, which now rubbed off the board, but we can remember what they are. Specifically, what we're going to do in the proof, and I just started here just to get the basic outline going, is so we've got a B, which is a subset of C, and what we'll show is that if either of the implications of this if and only if fails, then it cannot be the case that B is semi-decidable. So we prove that if either implication of, let's call it star, this if and only if, star fails, then B is not semi-decidable, which means that the index set by B is not computably enumerable. Index set of B functions of B is not computably enumerable, hence B is not semi-decidable. And basically, each of these arguments is going to be based on defining some contradictory some function that performs the reduction, again, using our friend the SMN theorem to do so, and both a bit similar to what we did in Rice's theorem. We're going to start with the trickier case, and then the other one will be able to clean up quite quickly afterwards. So the first case is we're going to assume that the left to right implication fails. So for case one, the left to right implication fails. Okay, we've got some set B, but it doesn't satisfy the left to right implication here. So what that means is we have some F in B for which, so this condition for all F fails, so there exists some F in B for which this doesn't hold. So i.e., we have some F in B such that, and we'll keep this F and use it, but such that it holds that for all finite subfunctions of F are outside of B. So such that for all finite F prime subfunction of F, I'm saying it's finite there, it holds that F prime does not belong to B. So notice that F cannot itself be a finite function, because if it were, then we would use F prime equals F theorem. F is necessarily not a finite function. Sorry, I said left to right implication, but we'll just write it like that. Left to right implication. Okay. So we want to use this F that we've got. I hope I call it F in the. Yes, I do. In the notes. We want to use this F in order to define some reduction, and we'll see how that works. But in order to do that, we're going to use the halting set again, which is a computably enumerable set, but we need to not just use the halting set as a black box. We need to sort of go into a little bit of the workings of the halting set. And to do that, we remember from last week that because K, the halting set, is computably enumerable, we can exhibit it as a search problem for a total computable function, finding zeros of a total computable function. So because K is CE, there is some total computable binary function such that a number number x belongs to K if and only if there exists some natural number y. Well, actually, I call it z in the notes, so let's keep consistent with the notes, such that tx equals 0. Okay. So we did all computably enumerable sets can be represented as search, as sets that for which there exists a 0 that you can search for, as we did last week. But actually, in the case of the halting set, there's a particularly easy way of understanding this, which is we can think of T as the decidable test that given an x in the halting set, well, sorry, given an x as a number, we run the Turing machine, so we think you're viewing it as an index E. We run the Turing machine represented by the index E on itself, E, as an argument, and we compute it for Z steps. So we use Z as a step counter, computing it on the Turing machine, and at the end of Z steps, we can see, has it halted in exactly Z steps? And if it halts in exactly Z steps, we set T, X, and Z to be 0, otherwise we set it to some other number, not 0. Okay, and then a number, of course, is in the halting set if and only if that computation does halt, in which case, of course, there exists some z for which d of x z equals 0, namely z is the precise number of steps on which the computation halts. So that's an intuitive way of understanding what this little t function is doing in this case. It's one way of understanding what you could do. So now, again, we're going to define. So we're going to define maybe the opposite. No, I'm not going to have enough space to finish on that panel. So that's, sorry, I'm going to put this at the bottom of the board here. So we're going to define a computable partial function in 2 arguments, and again, then use the SMN theorem to reduce it to 1 argument, to define it in its second argument as a unary function. So we're going to define a computable partial function, which we'll call G, and G of X, we'll call its second argument Z, because it's going to relate to the Z that we've got here. So the point is with this is we force G to be like F in its first argument. No, sorry, in its second argument, F of Z. The second argument, F of Z, if yeah, sorry, this has nothing to do with this set. It doesn't matter. I thought my notes were more sensible. More sensible notation, but they don't. Anyway, let me just write this down. 0 less than equal to y less than equal to z. So we search all numbers between 0 and z, and if we find, and if we all numbers y between 0 and z, and if we don't find 0, we return f of z. And if we do find 0, then we make this undefined. And this is perfectly computable because obviously when you get x and z as an argument, this is finite amount of search that we're doing between 0 and z. For each one, we're applying a computable total function to it. So we'll get a finite number of answers. We can check if they are all different from 0, and if they are, we return f of z. Otherwise, we don't. Otherwise, we're undefined. And again, we use the SMN theorem to reduce this to a unary function in Z, extracting the index from that unary function using the SMN theorem to get a total function on X to give us the index. So, by SMN, there is total computable S from N to N such that S is giving us an index for the function G x of Z. Okay. Sorry, that should be as publicly Z there. Again, in argument Z. Once again, we're going to see this gives us a reduction that will tell us that, just like in the proof of Rice's theorem, in this case, that phi of B is not computably enumerable. So, how do we get that? Well, we look to see if S belongs to K, then what do we get? If S belongs to the halting set, well then what happens if S belongs to the halting set, then there does exist some number Z for which T of x of Z is 0. And we see that f of Z is defined only for Z, sorry, well, we've got two Z's here. There's some number W, let's say, such that T of x of W is 0. And then phi of S of Z is defined only for Z strictly less than W, because as soon as we hit the 0, then for any higher number Z, this is not going to be, this is going to fail, and so we're going to the second clause. So we get that if S belongs to K, phi of S of x is finite. It's finite. And of course, by definition, it's clear that phi of S of x, so phi of S of x of Z, it's clear that phi that for all it's clear that for every x, then the function Z maps, for every x, the function Z maps to P of x of Z. This is a subfunction of f because of how it's defined here. It's clearly a subfunction of f. It's whenever it's defined as increasing f. So this is finite and less than a subfunction of f. So we've got that for all finite subfunctions of f prime does not belong to B. So f prime does not belong, so this function does not belong to our set B. So in other words, its index, S of x, is not in the set I of B. So its index, S of x, is not in I of B. Because phi of S of x does not belong to B. Okay. On the other hand, if S does not belong to K, let's write it like this, that if, sorry, this should be X, not S. If X does not belong to K, so in other words, if X is the complement of K, in that case, well, in that case, if it doesn't belong to K, there is no Z such that T of x of Z equals 0. So in that case, this condition is satisfied for all the Z, for all Y. Whatever we have for Z, this condition is satisfied for all Y. And so we always end up returning f of Z. So in that case, this function in the for that x in the argument Z equals f. So in other words, in this case, phi of S of x equals f, which implies, well, we assumed at the start that we found f at the start as belonging to B, so that means that S of x belongs to I sub B, because it's f equals to B. Okay, so what we have here is we have, if x belongs to K, then S of x doesn't belong to IB, and if x doesn't belong to K, then S of x does belong to IB. So in other words, we're reducing the complement of K to the set IB. So S is a total reduction, so reduction of complement of K to IB. But remember, total reductions, if you can reduce a set to a computably enumerable set, then the set you're reducing is also computably enumerable. So if IB were computably enumerable, then the complement of A would have to be computably enumerable, but we know it's not. Okay, so by the reduction lemma, now this time part 2, one of our computably enumerable sets, IB is not computably enumerable because we proved last week that the complement of K is not computably enumerable, i.e. B is not semi-decidable. Okay. And we're done with case 1. Okay, but we still have case 2, and for completeness, I'm going to do it. The argument is going to be very similar, but it's shorter. I mean, it was better to do the long one first. So let's screen the board. Right, so now we assume the right to left implication fails. So if the right to left implication fails, well, what that means is we have so there's some function in C for which the right to left implication fails. So we have some finite function and a superfunction of it such that the finite function belongs to B, but the larger one does not belong to B. So i.e. we have some finite f prime and also, well, that'd be, I don't want to put, we have some f prime, which is a subfunction of f with f prime finite, and for which f prime belongs to B, but f does not belong to B. And we want to again get a contradiction for this. So again, we're going to define some 2-argument function G, reduce it to a 1-argument function, and show that using the SMN theorem, and show that the total computable function S in the SMN theorem is a reduction of the sort, of the complement of K to IB, just as before. So this time we define a computable partial function, which again I call Gx of z. So this time G of x of z is defined to be f of z if z belongs to the domain of f prime, or x belongs to k, and otherwise it's undefined. And once again, this is computable because in this case, sorry, this should be Yeah, no, that's right. Yeah, that's right. So given x and z, how do we check if z belongs to the domain of f prime? Well, we simply apply the computable function f prime to z and wait to see if it terminates. How do we decide if x belongs to k? Well, we've already seen that. You simply run the computable partial function phi of x on the input x and wait to see if it terminates. Here we've got an or here, so we need to do these two things in parallel, and if either of them terminates, we say, okay, terminates, and then we apply f to z, which may or may not, in the first case, is guaranteed to terminate because f is a super function of f. In the second case, it will not. And otherwise, we're undefined. Anyway, we can see that's computable, and again, by the SMN theorem, I think it leaves us exactly as it is. That's very handy. By the SMN theorem, we have exactly the same as before, that there's a total function S that can be given an x, computes an index for the unary function in Z of G maps to G, Z maps to G of Z. And once again, we just check to see what happens. So in this case, it's clear that f prime is a sub-function of f, because whenever we output an answer, it's sorry, no, nothing to do with that because it's up here. F prime is a sub-function of f. The definition of G gives us, we have, in this case, if x belongs to k, then what happens? So if x belongs to k, well, then the second part is always true here of this condition. If x belongs to k, so we're always in the first clause, and we're simply returning f of z for any z. So this is always returning f of z. So that means that phi of s of x equals f, which implies that, well, f was not in B. Sorry, I'm pointing to the wrong place. Yeah, f was not in B. So that means s of x does not belong to I of B, the index set of B. Because f B. If x is in the complement of k, well then what happens also now? This part's never true. X is in the complement of k. So for any z, well, we return f of z if z is in the domain of f prime. Okay? But if z is in the domain of f prime, then f prime of z equals f of z because f prime is a subfunction of f. So that means we're returning f prime of z exactly for those z that are in the domain of f prime. In other words, phi of s of x is the function of f prime. Function f prime. And, of course, f prime was in B. So s of x, this means that s of x is in the index set of x. Because f prime belongs to B. We're now seeing in this case, what have we got? We've got a reduction of the complement of k, once again, to the index set of B. But again, S defines a reduction from k prime to B. So again, the same argument as before, I of B is not CE, hence B is not. It's not semi-decidable. Now we're really done because we have shown that for any set B of computable partial functions, If either of these implication fails, then the set B is not semi-decidable. Okay, that's it for today. Questions? Okay, so I wish you a nice week ahead and see you next week.